I welcome you all for this presentation. In this presentation, we are going to discuss about some of the concepts in number theory. This is the overview of this presentation: devices, then properties of divisibility, then division algorithm, then greatest common divisor, modular arithmetic operations like modulo 8 addition, modulo 8 multiplication, then modular arithmetic properties. Then we are going to discuss about two important algorithms, that is Euclidean algorithm and extended Euclidean algorithm. Then I have given you some problems to practice also, followed by summary of this presentation. First is devices. All are whatever you studied in school days, that is first, second, third standard. The same thing only we are going to discuss. Why we are discussing here in the sense all the cryptographic algorithm main base is the mathematical concepts only. So we are just recalling it, not we are learning new. You are just recalling or revisiting it. That's it. So here we say that a non-zero number B divides A if for some M have A equal to MB. Here all A, B and M are integers. That is B divides into A with no remainder. Then only we are calling it as B divides A. B divides A. Meaning is, say for example 8 divided by 4 means what we are telling is 4 divides 8. This way we are calling. 8 divided by 4 means we are calling as 4 divides 8. And here we are calling that B is a divisor of A. B is the divisor of A. So only B divides A. B is a divisor of A. What is this A? It is a dividend. So example is 1, 2, 3, 4, 6, 8, 12, 24 all divide 24. The meaning is 24 divided by 1, 24 divided by 2, then 24 divided by 3, 24 divided by 4, likewise it goes on. So here some other examples are 13 divides 182, minus 5 divides 30, 17 divides 289, then minus 3 divides 33, then 17 divides 0. These are some example. Divisors already you know. In any division we are having a divisor, that is the denominator, and the numerator we are calling it as dividend. But here how we are calling is the divisor divides the dividend. That is B divides A. B is the divisor and A is the dividend. Then we can look into some of the properties of divisibility. That is, if A divides 1, then A equal to plus or minus 1. And if A divides B and B divides A, then A equal to plus or minus B. Any B not equal to 0 divides 0. If A divides B and B divides C, then A divides C. Example, 11 divides 66 and 66 divides 198. So 11 divides 198. What this property we call it as? It is a transitive property. So already in maths you have already studied in discrete structures and all. It is a transitive property. If B divides G and B divides H, then B divides Mg plus Nh. Some coefficient we are having or some constants we are having. So the linear combinations for arbitrary integers m and n. Example, B equal to 7, G equal to 14, H equal to 63, M equal to 3 and N equal to 2. Then we can write that 7 divides 14 and 7 divides 63. Hence 7 divides 168. How 168 means 42 plus 126. So multiplication or some multiples or some, if some constant or coefficient is included means also we can perform the divisor or divisibility operation. So these are some of the properties of divisibility. Next is a division algorithm. In any division algorithm, we are having 4 ingredients or 4 components. Already we have discussed 2 components. One is the divisor and another one is the dividend. In addition to that, the result. What result we are getting is, if we divide A by N, we are getting the integer coefficient Q and integer remainder R. So we can write A equal to Qn plus R. So where 0 less than or equal to R less than N, Q, the quotient is floor of A divides N. Floor in the sense you know that floor of A divides N. Say for example 5 divided by 2. Floor of 5 divided by 2 is not here. 5 divided by 2 is, it is 2 only. Suppose if you are telling that seal of 5 divided by 2 means it is here 5 divided by 2 means it is 3. Floor and seal. Floor means you have to remove the decimal point. Seal means up. You have to round it off. That is the difference between floor and seal. And here what we are taking is the coefficient is floor of a divides n. That is very, very important. And the remainder, or we are calling it as a residue. Remainder is called as residue. So here you see the pictorial representation. Here 0, then n, 2n, 3n, likewise it goes on qn, a, then q plus 1 into n. Here the remainder is this qn between qn and a. So here the remainder is a equal to qn plus r. A equal to qn plus r. So here this n, that is r lies between 0 and n. 0 less than or equal to r, less than or equal to n. So by looking into this example, 70 equal to 4 into 5 is 10. That is here what we are doing is, we are doing 70 divided by 15. So 70 is the dividend equal to the quotient 4 into 15 divisor plus the remainder 10. So here we are having this 10, the remainder 10. So the remainder is called as residue. Next, why we are looking into these things means we have to find out the GCD of two numbers, greatest common divisor. So only this divisor, the divisor concepts we have looked into. Now we are going to look into the GCD, greatest common divisor. This also you studied in some 4th standard or 5th standard. So while computing the GCD, what we do, we just find out the factors, and whichever factor is common to both the number, that only we are taking it as the greatest common divisor. So this is a very common problem in number theory. That is GCD of a comma b of a and b is the largest integer that divides evenly into both a and b. So GCD of 60 comma 24 is 12. GCD of 0 comma 0 is 0. So we want no common factors except one if we define such numbers as relatively prime. That is GCD of 8 comma 15 is 1. If a GCD of two numbers is 1, then we are calling those two numbers as relatively prime. In future it may be used. So GCD of two numbers is 1 means those numbers we are calling it as relatively prime numbers. Let us look into one example. GCD of 1970, 1066. Here 1970 is written as this one dividend dividend is there. 1970 is the dividend and 1066 is the divisor. So dividend equal to quotient into divisor plus remainder. Then what you have to do, this divisor you have to take it as dividend. Repeatedly you have to do. So this is GCD of 1066 comma 904. Next you have to take the quotient as dividend, then this remainder as divisor. Then you have to find out the GCD of these two numbers. Not these two numbers, the remainder you have to find out. Plus the remainder we are having. So we have to find out already we have find out the GCD of these two numbers, only we are writing like this. Then we have to find out the GCD of these two numbers, that is 904 comma 162. The remainder we have to find. Then again what you are doing, this quotient you are writing here, the remainder writing here, then you are finding the quotient and remainder. Likewise it goes on. Quotient, then remainder, then again you have to find out the new quotient and remainder. Likewise you have to check. Finally we are getting 0 here. Once you get the 0, then this what is this value? If 0, this remainder we are calling it as GCD of these two numbers. So the final step we are getting as 0, the remainder as 0. Then only we are stopping the procedure. Then we are traversing back, and the previous steps remainder we have to consider the GCD of two numbers. So here GCD of this number is 2. You can use any GCD calculator, online calculator also, to check whether the value is correct or not. So within a fraction of second you can find the answer using the online calculators, but you know how to compute these values. This is very, very important. This is Euclidean algorithm we have used to find the GCD of two numbers. Later on we can see the algorithm. So another example is, this is somewhat very big number. So we are writing dividend, divisor, quotient and remainder. Whatever the procedure we have did there, same thing only here also we are doing. But we are splitting it into dividend, divisor, quotient and remainder. But same procedure you have to follow. Finally, we are getting the remainder as 0. Here remainder as 0. So how you have to find out the answer of the GCD? Previous steps remainder. So here it is 10978. So the GCD of these two number is 1078. This is the answer. So if time permits, you please work out and check whether this answer is correct or not, all the computations. Next is modular arithmetic. So here we are defining a modulo operator. Already in Caesar cipher itself we are learning about the modulus operator only, using the modulo operator only. But here only we are defining it. We are defining the modular operator, that is A mod n, to be the remainder when A is divided by n. So we are dividing, A is divided by n, then we are getting one remainder. That residue or remainder we are calling it as B. That is the answer. So here n is called the modulus, mod 26. N is called the modulus. 5 mod 26. What is 5 mod 26? That is 26. 5 mod 26 is 5 divided by 26. That is A mod n means A is divided by n. So 5 divided by 26. So it is 5. So B is called the residue of A mod n. So we can write A equal to Qn plus B. This way also we can write. That is, this is the dividend, then the quotient, then the divisor plus the remainder or residue. Usually we have to choose smallest possible remainder as residue. That is always the residue lies between 0 and n minus 1. So this process we are calling it as a modulo reduction. That is minus 12 mod 7. So always the remainder lies between 0 and n minus 1. Here it is mod 7. Mod 7 means it lies between 0 and 6 only. But here your answer is 12. So what you have to do? We have to perform addition. Minus 12 plus 7, which is equivalent to minus 5. Again negative number. So minus 5 plus 7, which is equivalent to 2. So we are writing 2. So again if you want to increase means you can do it. Plus 7. So 9 mod 27. But always the residue must be lies between 0 and n minus 1. So this you have to stop it. This you have to remove it off. Another concept is congruent. A and B are congruent. When we are telling that two numbers are congruent to each other means A mod n is congruent to B mod n. If both are equal, then only we are calling it as it is a congruent. That is when divided by n, A and B have the same remainder. Both have the same remainder, then only we are telling that congruent. That is 100 mod 11 equal to 34 mod 11. Meaning that 100 is congruent to 34 mod 11. So this is the congruent. So here we have learned some new terms: congruent, residue, modulo. Next is modular arithmetic operations. So we can perform some arithmetic operation with the residues, that is the remainder. That is, here we are using a finite number of values and loops back from either side, that is Zn equal to 0, 1 up to n minus 1. And the modular arithmetic is when we do addition and multiplication and we modulo reduce the answer. So we are doing reduction at any point, that is A plus B mod n equal to A mod n plus B mod n again mod n. So always the residue must lies between 0 and n minus 1. So how many reductions is possible, we can perform it. No issue in that. Here we are describing the operations with respect to some example. Here you see that we are having A mod n plus B mod n equal to A plus B mod n. A mod n minus B mod n equal to A minus B mod n. And A mod n into B mod n equal to A into B mod n. Here if time permits, you please try to work out these examples and find out. See here 11 plus 15 mod n. Mod 8. So here we are having 11 plus 15 is 25 mod 8. So we can write like this also, 2 into 11 plus 15 mod 8, that is 26 mod 8. This way also we can write. Finally anyway we are getting as 2 as the answer. So 11 plus 15 is 26. 26. that is 4 8s are 3 8s are 24. So 24 plus 2, 26 only. We are getting the answer as 2. So this way we can perform the operation. For the minus operation also we can perform. If you are getting the negative answer, what we have to do is minus 4 plus 8. So we are getting 4. This 165 mod 8, we have to divide it and take the residue. It is 5. Next is modulo 8 addition. In modulo 8, what we have to do is, in the row as well as column, it is 8. So 0 to 7. We have to write the value in the row as well as column. Then we have to perform addition. 0 plus 0 is 0. 0 plus 7 is 7 only. Then 1 plus 0, 1. 1 plus 1, 2. Likewise it goes on. And 1 plus 7, it is 8. So 8 modulo 8 is 0. So here we are having the 0 as a inverse. So here we are having 0. Because always the value lies between 0 and 7 only. So now we are getting 8. So it is 0. So wherever we are having 0, that becomes the additive inverse of that particular modulus operation. So here 1 is the additive inverse of 7, 2 is the additive inverse of 6, 3 is the additive inverse of 5, 4 is the additive inverse of 4, 5 is the additive inverse of 3, then 6 is the additive inverse of 2 and 7 is the additive inverse of 1. So this way we can have the additive inverse. If you are performing modulus operation, if you are getting 0, then it is a additive inverse exists. Suppose we are getting 1 in the multiplication, then their multiplicative inverse exists. Let us see that. Here you see modulo 8 multiplication. This is multiplication. So here you see that the row we are having the row as well as column we are having 0 to 7 because it is a modulo 8 multiplication. Then we have to perform multiplication. 0 into 0, 0. 0 into any number it is 0. So this row fully 0. Then 1 into any number, that number. So 1 into 1 is 1. So here we are having the multiplicative inverse. Next 2, we are not having any 1. So there is no multiplicative inverse exists. For 3, 3 into 3, 9. So 9 mod 8 is 1. So here we are having the multiplicative inverse. 4, no multiplicative inverse. 5, 5 into 5, 25. 25 mod 8 is 1. So here we are having the multiplicative inverse. For 6 also we are not having it. 7 also we are not having it. So we are having for 1, then 1, 3 and 5 we are having the multiplicative inverse. 7 sevens are 49. So 49, 7 sevens are 49. Here also we are having the multiplicative inverse. For 7 also we are having the multiplicative inverse because 7 sevens are 49. 49 mod 8 is 1. So 7 also we are having the multiplicative inverse. Next, some of the properties of modular arithmetic, commutative law, that is we know that w plus x mod n equal to x plus w mod n. With respect to plus as well as multiplication, this commutative law holds. Then associative law, w plus x plus y mod n equal to w plus x plus y mod n and w into x into y mod n equal to w into x into y mod n. So distributive law also holds for this addition and subtraction, addition and multiplication. That is w into x plus y mod n equal to w into x plus w into y mod n. Identity 0 plus w mod n equal to w mod n and multiplicative identity is 1. So 1 into w mod n equal to w mod n. Then we are having the additive inverse, that is for each w belongs to z and there exists a z such that w plus z equal to 0 mod n. These are the modular arithmetic properties. Next is the Euclidean algorithm. Already we have seen the example of this Euclidean algorithm to find the GCD of two numbers. Mainly Euclidean algorithm is to find the GCD of two numbers. It is an efficient way to find the GCD of two numbers. Here we use the algorithm GCD of a comma b equal to GCD of b comma a mod b. So how we are performing this algorithm means Euclid we are calling Euclid of a comma b. If b equal to 0, then we have to return a, else return Euclid of b comma a mod b. So repetitively we are performing the GCD operation in the example. The same thing only here it is given in the algorithmic format. So here we are having the flow chart of this algorithm. We are just starting it. If a is greater than b, no means you have to swap a and b. Always you have to check the two numbers whether the first dividend is greater than the divisor or not. You have to check it. Then if it is not, then we have to swap it. So suppose if A is greater than B, then what you have to do is we are dividing A by B, calling the remainder R. Then we are checking with the remainder R. If R is greater than 0, no means this GCD is the final value of B. If it is yes, we are replacing A with B, then we are replacing B with R, and again we are performing the division operation. So this is the representation of the illustration of this Euclidean algorithm. That is, we know that any number, any dividend and divisor if you are having, we can represent with respect to dividend equal to quotient into divisor plus R. So here we are performing repetitive calculation. So remainder R1 equal to A mod B. Here we are having R1. Then R2 equal to B mod R1. Here we are having R2. R3 equal to R1 mod R2. Here we are having R3. Likewise it goes on. Next is extended Euclidean algorithm. So this Euclidean algorithm just calculates the GCD of two numbers only. But this extended Euclidean algorithm calculates the extra two values, that is x and y. It just calculates the GCD, also it calculates the x and y value. So these values can be used to find the inverse of a number. If GCD of two numbers is 1, then only inverse exists. So if inverse exists, using this x and y value, we can find out the inverse of a number. So ax plus by equal to d equal to GCD of a comma b. This is for the extended Euclidean algorithm. Where we are using this extended Euclidean algorithm means it is mainly useful for the crypto computations. In many of the cryptographic algorithms, in most of the cryptographic algorithms, inverses we have to find and we have to use it. In those places, this extended Euclidean algorithm can be used. So it follows the sequence of divisions for GCD, but assume at each step I we can find x and y. That is R equal to ax plus by. At the end find GCD value and also we have to find the x and y. This is very important. If GCD of a comma b equal to 1, these values are inverses to each other. Let us see one example. Before that, how to find the inverse using extended Euclidean algorithm. Here we are calling the Euclid algorithm, extended Euclidean algorithm, m comma b, two parameters we are passing. Then we are having a1, a2, a3, 1, 0, m. So if you look into the example, it is very easy to understand this algorithm. First let us see the example, then we can go through this one. So here you see using extended Euclidean algorithm, we are going to find out the GCD of these two numbers, plus we are going to find out the value of x and y. That is, we are going to find the GCD of 1759, 550. So first step what we have to do is, if the GCD of these two numbers is 1 or not. If the GCD of two numbers is 1, then only inverse exists. So here you see, if we are getting a remainder 0 in the last step, we have to stop it. Then which one we have to take it as a GCD? The previous step's remainder we have to take. Here the previous step remainder is 1. So this GCD of these two numbers is 1 only. This step you have to do which is similar to that of Euclidean algorithm. But here in the extended Euclidean algorithm, what is the extended thing means? Finding out the value of x and y. So here always these first two steps you have to do for all the problems. This is very important. So I equal to -1, at that time you have to write the biggest value, because in Euclidean algorithm we have seen that if the dividend is not high compared to the divisor, then we have to swap it. If two numbers are given a and b, if it is the dividend is not higher than the divisor, then we have to swap it off. So here -1, there you have to write the bigger value. So in the -1th position we are having xi equal to 1 and yi equal to 0. Then for 0, I equal to 0, you have to write the divisor. There you have to swap this value, xi equal to 0 and yi equal to 1. Then we have to perform this operation. See here, x minus 1 equal to 1, y minus 1 equal to 0. x naught equal to 0 and y naught equal to 1. See the reminder, r minus 1 is a and r naught equal to b. So from next step on, we have to perform these things. R1 equal to a mod b. Here you see R1 equal to a mod b. 1759 mod 550. So we are getting the answer as 109. And what is the quotient? It is 3. So how we are finding out the xi and yi value? This formula you have to apply. X1 equal to x minus 1. Already you know x minus 1 value. Minus q1 into q1. Where is q1? This one is 3 is the q1 value into x naught, which is equivalent to 1. Then y1 equal to y minus 1, which is equal to 0, minus q1 3 into y naught, which is equivalent to 1. So what is it is minus q1, that is y minus 1 is 0, minus q1 is 3, then y naught is 1. So it is minus 3. So q1 is 3, so here we are getting as minus 3. Likewise, you have to find all the values, and finally the yi value we are obtaining, the positive value we are getting. This is the inverse of these two numbers. 355 is the inverse of 1759 and 550. So in order, before performing these steps, first you have to apply the Euclidean algorithm and you have to check what is the GCD of two numbers. If GCD of these two numbers is 1, then only the inverse exists. Then only you have to proceed it. Otherwise, it is waste of time. Always you have to keep this in mind. And I have given you two problems to practice. You have to use the extended Euclidean algorithm to compute 17 inverse mod 26 and 17 inverse mod 23. So in this presentation, we discuss about the number theory concepts like divisors, properties of divisibility, then division algorithm, then greatest common divisor, then modular arithmetic, then modular arithmetic operations. There we discuss about modulo 8 addition and modulo 8 multiplication. Not only for 8, for any numbers if it is given, you must be in a position to do that table. Then modular arithmetic properties. Then we have discussed two main important algorithm, Euclidean algorithm and extended Euclidean algorithm. Euclidean algorithm is to find just the GCD of two numbers. Extended Euclidean algorithm is to find out the GCD of two numbers plus the inverse of the given numbers. In the next presentation, we will be looking about one of the substitution technique that use this inverse concept. Thank you.